Control systems theory is an important part of today's technological advancements. The control system theory and its applications are used in everything from simple machines like your flushing toilet to complex systems like an electric car or even the International Space Station. In fact, electric cars are nicknamed computers on wheels due to the crucial role the controllers play in governing their performance. In this video, we will explain the fundamental concept of control theory using the example of a drone. A control system is basically a collection of mechanical and electrical mechanisms that operate together to provide a desired response. A quadcopter drone consists of 4 rotors attached together in this fashion. The rotation of the propellers generates an upward thrust. Each individual rotor's speed can be controlled independently, thus paving the way for accurate direction control. Many different sensors are required to measure the drone's position and orientation. Some of them include an accelerometer, a gyroscopic sensor, flight cameras, timers, and so on. The drone can achieve translational motion in 3 axes, and it can rotate in 3 dimensions: roll, pitch, and yaw. Let's consider the scenario of a drone hovering. Your aim is to keep the drone hovering steadily as shown. For a drone to hover in the air, the upward thrust must balance the downward pull of gravity. Additionally, the net torque should be 0 to prevent it from spinning. That's not all. The translations and angular velocities in all 3 directions also should be 0. Let's see how the control system is applied in action. This drone was hovering in the air happily when suddenly the wind blew and the drone tilted as shown. The drone's smart controllers have to get the drone back to its normal angle, but the question is how? Let's freeze the scene at a particular time when the wind is blowing. Here, we're considering a change in just one angle for simplicity of analysis. Using a few sensors, the drone can measure its speed of rotation, its direction, and its angle. The sensors then feed this data back to the system. The angle theta is the error with respect to the horizontal axis of the drone. In order to successfully reduce this error, the propellers should produce a torque opposite to the angle. When the left and right blades spin at different speeds, the propellers will produce a different force and torque. The controller has to find suitable values of propeller forces throughout the restoration process. You can see that by the end of the restoration, the propeller forces become equal. Using a simple force analysis, the forces that the left and right propeller pairs have to produce can be connected to the angle as shown. Don't worry if you can't understand all the variables in this equation. You just need to understand that the force values should vary with the error angle. However, this problem is not solved simply by making the error angle 0. You have also to make sure that the angular velocity of the drone at 0 degree is 0. If the angular velocity is not 0 at the 0 angle, the drone will rotate in the opposite direction, as shown. Let's plot the angular velocity that the drone has to follow in an ideal restoration process. Initially, due to the wind, the drone had an angular velocity, as shown. This velocity decreases slowly due to the torque produced by the propellers. After some time, the velocity will reach 0 and then go negative. It is during this period that the drone starts to journey to a 0 angle. Like we explained previously, as it approaches the 0 angle, the velocity also should become 0. This means the previous force equation we derived should follow the constraint of this graph throughout the solution. This is not an easy equation to solve using calculus, which is why Laplace transforms play a crucial role. The Laplace transform of this equation yields very simple polynomial terms, which solves the equation with ease compared to the differential equation. In our case, we will be able to find out how the forces should vary with time. Laplace transform is a mathematical operation which converts a signal that lives in the time domain to the frequency domain. It provides us with a view of the system's reactions to input signals' different frequencies. Think of it as looking at the entire electromagnetic spectrum to gain more information about a galaxy instead of only using visible light. Since Laplace transform produces algebraic equations, they can be solved quite easily. To get the final output, what you have to do is just take the inverse Laplace transform of this solution. Coming back to our drone, during the disturbances, usually all the three angles will vary rather than just one at a time. The sensors will constantly monitor the position of the drone and feed it back multiple times per second. Every cycle further reduces error. Advanced control algorithms are incorporated into such systems to increase accuracy and efficiency. In this drone example, we have seen that the feedback information controls the drone's motion. This type of system is called a closed-loop control system. Similarly, an open-loop control system also exists in which feedback is not present. Think of how an electric hand dryer blows out hot air when it detects that your hand is present. It stays on for a set duration of time, regardless of how dry your hand is. It gives no feedback about the dryness and makes no adjustments at all to make sure your hand is optimally dry. Control system logic has been in use since ancient times. Evolving with technology, this remarkable field has truly transformed our society for the better. Thank you for watching the video.